Today we're going to talk about how to achieve success with your CCS initiatives. Okay, so brief agenda for the day. So we're going to start with a quick overview of carbon capture and sequestration project goals, what the main challenges are. Then we're going to introduce our approach, which has an integrated model for CCS. We're going to go over 3 customer cases, and then we're going to have some discussion, some next steps to consider in your CCS journey. So CCS project goals, as any project, is to be profitable and technically viable. So our objective is always to, as early on as possible, define accurately the system-wide operating conditions. We're always looking for ways of reducing CapEx and OpEx and have sustainable operations. Because we're talking about CCS, we have to be very, very aware of penalties on missing injection targets. So reduction of in-loss profit events, it's a key factor. Also, we want to be fast to market. We want these projects to go at a fast pace from conception to operation. And we always want to reduce downtime and increase our official runtime. One challenge that we have here is that we want also to enable the project to be flexible for future market needs. We don't want projects to be in case on the immediate solution for the immediate problem. We want projects to be flexible to withstand the test of time. All of this is for nothing if we cannot do our projects and operations in a safety way. So having insights in the system is going to enable us to provide better assurance that the environment, material, and personnel are reduced. So what are our main challenges in CCS projects? Well, it's an emerging market. We have right now issues like low profitability. We have lack of operating data and experienced personnel. And also we have increased scrutiny by not only regulators, but also the media and the global population. So we have the impacts of impurity, which is complex and affects both thermodynamics and hydraulics. We then have the approach that project teams or the projects themselves have, which have siloed disciplines with sometimes competing goals. Having accurate and good quality estimates on early stages, always an issue. And then we have the problem with accuracy of the design conditions versus the actual operating conditions once the system is built. So what are the main consequences? Well, we have increased operational costs because we design for conditions that are not occurring 100% of the time. We have increased risk. We're pushing our system beyond its design conditions. We can have increased downtime and penalties if our operating boundaries go beyond what was designed, and we have to stop operation for analysis and tuning. And throughout the process of the project, if we have to come and review and redo engineering, that means slower time to market. So what's our approach? Well, we propose building something that we call a BEAST. It's a basic energy-aware system twin, and it's an interactive model that combines the power of simulations and visualization. It facilitates a rapid exploration of the parameter space, so we can get better data, clearer understanding of the system, and comprehensive set of results earlier on the project. So our engineering team specializes in designing things like this, like the BEAST, and these are designed for getting accurately real-life full system post-construction conditions, reduce staffing demands, saving company money, and reduce risk inherent to specialized engineering scenarios. Why? We have a team of experts that have seen this problem and have seen similar problems in the past, so you don't have to waste time developing the in-house competence early on. So, going back to CO2 and why this matters. So, where the CO2 comes from is going to have an impact of the type of transport, the type of injection, and your conditions throughout the system. The impurities actually affect how the phase envelope of the mixture evolves. So we have here in black, we have here in the center, the pure CO2 equilibrium line. Once we start introducing impurities, these impurities expand that phase envelope, as we can see here with hydrogen, or in the bottom part with propane. So the source of these impurities and the source of the CO2 matters because it will impact our operating conditions. We have light impurities like hydrogen, nitrogen, methane, and normally we see those when we're talking about CO2 from hydrogen generation or ammonia, fertilizer plants, or direct air capture. We have heavier impurities, including solids and particles that come from pre-combustion, from pre- and post-combustion, metallurgical coke production, cement, or lime production. So knowing how these impurities impact is of paramount importance. Here we have a couple of examples of typical impurities. We go about, in this case, fertilizer, ammonia, or H2 production. We have high hydrogen. Going back, that's what expands our phase envelope upwards. We have nitrogen as well. On the other side, we have flue gas from desulfurization. We see that we have NOx and SOx. We have combustion from coke production, similar, but now we have also VOCs. So depending on the source of your CO2, you'll have to design your system in a slightly different way. Another vital aspect, and this leads back to the material design of the system, we have water. It's vital to know how much water you'll have on your CO2 stream. And this is to ensure that the system is designed so that no free water is present in the system under operating conditions. And depending on your ambient conditions, if you're going through, if you're in colder climates, you'll have stringent restrictions on water. And here, for example, you see how the impact of going from 50 ppm to 500 ppm content of water. So, for example, in colder places where we can drop below 0 Fahrenheit, we cannot have water content of 100 ppm because that will result eventually in water dropout with all the risk that it has associated with formation of acids. However, warmer climates, saying we're here in the Gulf, we might get away with something closer to 250. Again, it all depends on the material selected, but this is something that cannot be neglected. So, why do we say SMEs are needed for CO2 modeling? Well, off-the-shelf solution right now provide a fairly decent approximation of the thermodynamics of the CO2 mixtures. However, they're still not good enough. So here, for example, we have experimental data on CO2 hydrogen mixtures, and we see that off-the-shelf solutions, in this case, like the solid line, we see that for using the Penn-Robinson equation of states gives a very large underprediction of the pressure at which we have to face separation. So knowing these operating conditions is paramount to designing a safe system. So tuning, even though we have good solutions, tuning is always required to get precise operating conditions and resulting in an efficient system design. Continuing with this trend is not only the phase envelope, we also need to know exact properties of the fluid, in this case, for example, the density. So when we have the density, we see that the default variables can be between 10 and 15% lower than the actual values of the mixtures. Why is this important? If we design our system for, let's say, CO2 content of 5%, and our shutdown conditions in the well are determined by the weight of the column. So if the column is 20% lighter or 20% heavier, we're going to be in a different case. If, let's say, our initial prediction tells us that the column is all in single phase, all the wells in single phase, and in reality we have lower pressures, what can happen is that we'll have at the top of the well, we have some phase separation where the lighter components like hydrogen go to the top and the slightly heavier CO2 drops. Why is this important? Well, we'll have the material people crying about hydrogen embrittlement of the metal, because designing for 5% or 18% hydrogen is significantly different. For the pipeline, in a way, is slightly simpler. We have clear ways, clear regions where we want to operate. And depending on the system and the conditions, we might try to operate in dense phase, so above our phase envelope. And here's when it's important to know where your phase envelope lies. You want to be in single phase. There's all sorts of operational problems associated with multi-phase flow here in this region. Or we can operate in gas phase here below the critical point. So all this all this region here around the phase envelope, we have a single phase. Here we call this liquid, this is dense phase, here's gas. Inside we'll have gas and liquid coexisting. So we're talking about 1500 to 1800 psi here for the typical dense phase. And the problem we have is that normally insulation is required to keep these temperatures, especially when we have long pipelines. So, for example, accurate modeling of the H2 is critical, because it's not the same to need 1200 psi to stay out of multi-phase than needing 1500, let's say. So when we talk about designing the wells, going back to what was mentioned before, here in the US, we're dealing mostly with aquifers for carbon sequestration, whereas in Europe and Asia, we've seen more work towards depleted reservoirs for capture. So the differences are mainly we have for the aquifers, we have higher initial pressures, and then we have the water-filled reservoir, right? And in the depleted reservoirs, we have low initial temperatures and issues with JT cooling that can happen at the wellbore. So what are our main challenges on designing the wells? Where we have the temperature management, again, bottom hole temperatures, how much pressure we have to choke down at the wellhead. We have pressure management. We want to minimize CapEx and OpEx while allowing or making our system flexible enough to inject at different rates and under different conditions. So we want to avoid wasting energy in compression or pumping station, and we want to avoid high pressure ratings. We try to stay in single phase flow. There are some challenges associated with multi-phase. We can have vibration when we have the collapse of the bubbles. If we go from multi-phase to single phase, or in the case of hydrogen present in the CO2, we want to prevent the appearance of high H2 content phases, especially during shutdowns. All right. So what's our proposal? What are we suggesting now? Well, we need to keep in mind the system and design for the whole. We have wells and pipeline teams that have slightly different targets, and those teams need to be in constant communication, and they should be aligned in the objectives in the project. One thing is that designing for multiple wells increases significantly the complexity of the problem and reduces the viable operating conditions. For example, especially when we have asymmetrical injection, when we have one well getting more CO2 than the other, or we're switching zones or injecting at different zones with different pressures, or when we have startups, because wellhead pressures will be different. And unlike the production systems, wellhead pressures here have a great impact in the wellhead conditions. And we'll get back to that in the next slide. It seems confusing. During production, we have flow going from the reservoir to the facilities. So the wellhead conditions, upstream of the chokes, will depend only on the reservoir, the fluid, and the flow rate. And basically, we have fixed pressure and temperature of the reservoir. We lose some pressure when we go from the reservoir to the well. We have friction losses going up the well. We have the static head, and that gives us a final pressure and temperature. The density, which is what gives us is kind of how heavy the fluid is, will impact the frictional losses and the static head. But because the fluid is going upwards, every time we lose pressure, we're going to affect the pressure drop for the section above the one we're looking at. With sequestration or injection, it's slightly different. We're having flow go from the facilities to the reservoir. So our wellhead conditions, again, depend on the reservoir fluid and flow rate, but also on the wellhead conditions. And when do we have this circular relationship here? Well, because let's say we have a cold fluid versus a hot fluid entering the well. Even if reservoir fluid and flow rate are the same, the fact that my fluid is warmer or cooler will have a different impact on the density and then impact the losses, the static head, which will mean my wellhead temperature will be different. So we have this circular relationship here that cannot be ignored. And when we have multiple wells with competing targets, then it becomes a challenge to define wide range operating conditions. So going back to that, so let's say we fix the flow rates. Here they're represented by the M with the dots, and we increase the temperature. Well, our wellhead pressure will increase because our column becomes lighter, more higher temperature, lower densities. This also has some associated increase in frictional losses, but it's not as significant as the decrease in the static head. Let's say we have a fixed temperature and we increase the mass rate. Well, that increases also the pressure. So having all these parameters being highly correlated makes it difficult to define wide range operating conditions or precise operating conditions if we don't consider all the parts at the same time. So this is why the integrated design matters. So the potential issues are changing in operating conditions that affect different wells in different ways. It can be opposite. We have wells that are identical, but because they're brought online at different times, will have slightly different operating conditions. We also have an important thing that one well detects the pressure of the system. So changing conditions in this well affects the system as a whole. And also we can have required operating conditions that are very narrow and impose stricter conditions at the producing facilities. So what this leads to is narrow operating bands, maybe extra expenditure on capex, extra capex or opex on the facilities because we have a narrower target, and also difficult operation. If these changes are not accounted for in the project design, this can lead to downtime and then penalties because we're missing our injection targets. Ultimately, this can lead to damage to the facilities because our operating conditions go beyond what the equipment was designed for or the pipeline, and leading to the most important thing, safety. We're increasing the risk to both personal and material losses. So as mentioned earlier, we're proposing using a BEAST, a basic energy aware system twin. And it's a very simple methodology where we take our system, we do a quick inspection at the beginning to see how the different parameters interact. We split our system into its elements, in this case, wells and pipelines. We run a set of cases for these parts, and then we use simple mass and energy balance to connect the parts. What this allows us is to then develop interactive visualization so we can explore how the system behaves and foster deeper analysis. So why would you build a BIS? Well, it allows us to provide value as early as possible. It facilitates exploration, identification of non-viable scenarios, which is of paramount importance, and can reduce rework because we develop parts and we run the parts independently, the parts are reusable. If, let's say, we start exploration with a 20-inch pipeline and some finding results in the pipeline size being changed, we don't have to rerun the whole system and the whole analysis. We just rerun or add the data for the new pipe size. So it also allows us to explore easily different routes, incorporate changes, for example, and explore alternatives. It allows us to cover a wide range of operating conditions, and the end product, which is basically a dashboard, facilitates the exploration and the analysis of the results. And for me, as an engineer, as a consultant, this is very useful to me because it allows me to have more data available early on, and I can go around meetings without having to say, I'll have to run that. Give me a couple of days. Because we have most of the results readily available. So we've used this approach in sequestration injection system. We've used it for production. So for sequestration, we have cases where we have flow from an emitter into different wells. It allows us identification of operating conditions and get a better understanding of how the CO₂ project works. And in production, we have cases, for example, with several oil wells in a drill center connecting to a pipeline. So sizing and thermal design of the production system could be sped up. So how do we do this in CO₂ sequestration? We started with an integrated model that had everything, wells and pipelines. We conducted a few runs to get more of a feeling of how the parameters interact. And then we split our system, as we mentioned before, and ran large amount of parametrics. And because the system is smaller and simpler, we have, instead of having one pipeline with 5 wells connected and having to run a limited number of cases, we can run parametrics on the smaller parts of the system, which allows for a wider exploration. So that initial analysis of the build of the system helped us define flow rate, fluid inlet, temperature, and now the condition ranges for our parametric, and for the pipeline parametric, and for the well, it allows us to do quick analysis, changing the depth of the injection zone, the injectivity, the flow rate, and the wellhead temperature. So from the pipeline parametric, we get the available enthalpy and pressure at the different wellheads, and from the wells, we get the required pressure and enthalpy at the wellhead. And I go a bit into the detail of why we're using enthalpy or energy in this analysis. So this also allows the verification of several design constraints simultaneously. So to do all this, we generated our parametric analysis using flow tools with the different features that we have available right now. We then extracted the results, exported them to an Excel file, and loaded them to this data visualization software. In this case, we use Power BI to connect and integrate the results. So here we're going to go over 3 customer cases and one key takeaway for each of the cases. So we have our case 1 and the importance of using pressure enthalpy space for the analysis. The default way of looking at problem, which is normally pressure and temperature, is not enough. We need to use the enthalpy space to identify non-viable conditions. In our second case, we highlight the importance of considering all the parts at the same time. So having wells at different sites with different conditions with the same inlet, having different wells can have competing requirements depending on the rates and the pressures, and it also allows us to analyze the well requirements, how the well requirements change with time. And customer case 3, the key takeaway is, remember, systems are dynamic. So we need to keep in mind that pressure, temperature, and flow rate of the wellheads are not 3 independent parameters, and operating procedures and control strategies need to evaluate the effect of changing these parameters with a system-wide view. So going into the first customer case, use pressure enthalpy space. So enthalpy is to put it simply, it's like a measure of the energy of the system. So in this case, we have on the left, we have the normal pressure temperature space. That's the one we normally see and we normally talk about in designing the system. And we have the phase envelope of a CO2 H2 mixture. So all the dots we see here are well simulations, and the coloring corresponds to their status. So we have in dark green runs that were deemed successful, where we end up with viable injecting conditions. We have this low red, pink here, saying under these conditions, we end up with too high bottom hole temperatures that can cause stress issues at the bottom of the well. We have here this bright red where we have more than one problem, be it too high a pressure and temperature. We have these cases here that fall within the phase envelope. We have flashing. We want to avoid multi-phase flow in the well, so those cases would not be viable. And there are also cases where the bottom hole temperature is too low, and that can also lead to material problems. If we look at these same plots in pressure enthalpy space, and there's nothing much more to add, it's pretty much the same, we get the same amount of information. What happens when we include the data from the pipeline? Well, we see here these vertical and horizontal lines define the operating conditions of the pipeline at the injection point, and this is basically the operating point. In pressure, temperature, space, there's nothing extra that tells us, that gives us information on the system, rather, with the exception of these 3 points that were already bad. The pressure is too high because we require wellhead pressures higher than those of the pipeline. Or here we require more temperature than the fluid arrives with, so those cases are discarded. When we switch to pressure enthalpy, we see that actually we arrive under this condition at the pipeline. All these conditions to the right cannot be achieved unless we add energy to the fluid. Either we heat it or we compress it and get the pressure up. So these cases that before were apparently viable are actually not. So unless we consider the energy, we cannot define precisely our operating conditions. So here we have almost a third or even half of the cases that were deemed viable, now not viable. The other advantage of looking this in pressure enthalpy space is that the choking, where we knock the pressure at the wellhead, for example, or in an intermediate point, is depicted simply by a vertical line. So let's say our pipeline is operating at this pressure. If we need to knock the pressure down from this condition from 1900 psi to 1400, we'll just draw a vertical line. This line would be a sloped, curved line here in the PT space. So this already gives us a bit more information on how our system is behaving. All right, jumping to customer case 2, considering all the parts at the same time. If we have more than one well, the complexity increases because the well with the highest pressure requirement will fix the pressure of the whole system. So then we need to consider how is that change in pressure that will need to occur at the other wells going to impact. So here, for example, we have two different well curves. So this is different flow rates in the wellhead and what the required pressure and enthalpy is at the wellhead. And we see if we have our pipeline here, how the wells behave and where the wells are located will impact the system differently. For example, we couldn't set up a well at this intermediate location with these current conditions because our well requires more pressure. So having these wells, having several different wells makes us have to define a very clear and very precise operating envelope for the system. Also, one aspect here is changing. For example, we complete a well, there's a well that's forecasted to be injecting in different zones. So changing the zone a system well is injecting to can have a potential impact for the whole system. So what happens with time? So as time goes by, injecting into a well can change the resistance the wells offers to the fluid. In the case of aquifers, we have two competing events. The injection kind of increases the pressure of the aquifer a bit, but also the CO2, the presence of the CO2 makes the further injection of CO2 easier. So if the injectivity reduces or increases, it's going to change my operating parameters. And if we have a significant change, our once viable operating conditions can turn into non-viable. Another aspect, as mentioned before, changing the injection interval. So we say originally we're injecting, and the well curve would be this dotted line here. If we change the injection interval, now our well curve moves higher up and to the left. So we can have higher pressures, but we maybe require lower temperatures. So, all these aspects need to be considered early on, so we don't end up with surprises later on during operations. So the last customer case highlights the importance of remembering our systems are dynamic. So once we did our study with our beast, we canvassed the space. We all identify operating conditions. Then we can go back to a fully integrated model where our pipeline and our wells are modeled at the same time and conduct studies in things like shutdowns and restart. Sorry. So on this case, during normal operating conditions, we see that this is a pipeline and we have 4 wells. We have this well here at the end coming from a branch. So we see that this well in the center is the one that dictates the whole pressure for the system. And you see that all the other wells have some amount of pressure drop at the wellhead. And that's because this has the highest pressure requirement. So what happens? Well, we have to remember that all these pressure drops here have an associated temperature drop. So we have significant JT cooling, for example, in these 2 last wells. So what happens? Higher pressure drops lead to higher JT cooling, which means lower temperatures, which means our fluid is denser, and it furthers the requirement for pressure drop. So what did we learn about this system once we did all the analysis? Where in this case, for example, we had the different strategies for shutdown, depending on what the purpose of the shutdown was. So for shutdowns, where the intent is to reduce the CO2 inventory in the pipeline, we have something that's called we shut down the inlet first and we empty the pipeline to the well. So this scenario leads to multi-phase conditions quicker within the pipeline. But if the purpose of the shutdown is a repair, this is this is a consequence that will have to be dealt with. On the other side, if we're just shutting down to do some repairs on the wells, or there's some problem with the emitter and CO2 is no longer going to be available, we can shut the wells first and allow the system to pipe slightly. This will allow the system to stay in two-phase for longer and prevent multi-phase conditions with all the associated risks that were mentioned before. And for example, under long-term shutdowns, it might help keep the pipeline and the wells out of risk of multi-phase. Again, this will depend very heavily on your composition, so it's something to cannot be generalized easily. It has to be, it's very project dependent and composition dependent. In this case, for the research as well, the main target was to keep the pipeline in single phase. So in this case, what was concluded was that quicker restarts were favored because the quicker restart meant we shift the inventory in the pipeline quicker and we allowed the hot fluid to reach the wells faster. And these higher temperatures reach faster means that the wellhead pressures can be kept higher for longer, keeping the system out of multi-phase flow. So all in all, the main message from this one is that careful planning is required, and the sequencing of the process is critical, especially when the conditions in the system are close to those of multi-phase flow. So in summary, the Becze integrated model allows for quick exploration of the parameter space. It allows us to incorporate competing constraints and provides comprehensive set of results earlier in project life, give the team a better understanding of the system. This leads to improved system operability and reliability as we are designing in a more rigorous way. More specifically, in these cases, this procedure allows to clearly identify viable narrow operating ranges, highlight risk of multi-phase flow conditions at the wellhead. Again, we don't want to go with and have to deal with hydrogen embrittlement. And more importantly, having all these early on allows us to spend more time designing for better outcomes. So what are the benefits of our approach? Well, you get higher confidence on the operating band, and this reduced uncertainty leads to reduced CapEx and OpEx and streamlined operation. Reduced duration and severity of lost profit events. We have less unknown conditions, and we can plan for more scenarios, which allows for fewer penalties due to missing target, streamlined operation, and it prevents rework, which means faster time to market. It reduces the impact damage to facilities and environment. Operating conditions are well known early on and allows the design to be targeted to those and give insight to the system to provide better assurance that risk of loss of life are reduced. And also of importance, it enables flexibility for future markets. If we know ahead we can get different emitters to provide CO2, we can plan in more detail and explore the impact of blending CO2 from different streams early on and incorporate that into design. So conclusion, main remark is expertise and early investment in engineering analysis can help you reduce uncertainty, financial and physical risks. So having an SME for accurate thermodynamic parameter tuning and also a Becze and an integrated model allows you for more information earlier in the project, quick and accurate exploration of the parameter space, and all these results is reduced risk profile, both material, personal to the project and economical, and a higher performance sequestration system. So what can you do next? Well, you can give us a call and see how we can help you. We can also assist with project reviews and also help you identify drivers to increase the return on investment for your CCS initiative.